If you have been following tech news recently, you will definitely notice a strange phenomenon. NVIDIA's chip orders are endless. But why does Jensen Huang always say capacity is limited? Can't TSMC just build a few more factories? Actually, the problem isn't the chip manufacturing process, but the packaging of the chips. This is CoWoS, which the whole world is now scrambling for. But if you think CoWoS is just a technology that sticks chips together, then you are underestimating TSMC. To simultaneously satisfy high performance, low cost, and the three contradictory goals of massive size, TSMC has actually evolved three distinct variants. Today, let's perform a deep dive into CoWoS and see how these three musketeers support the entire AI era. Before diving into technical details, we must first understand why traditional organic packaging can no longer keep up. Imagine you have a super fast computing GPU like a Ferrari, but your data must be stored in the neighboring HBM memory like a warehouse. In the old packaging era, these two were packaged separately and then soldered onto the printed circuit board PCB. This creates three fatal problems. The distance is too long. The trace widths on a circuit board are usually dozens of microns. For an electron, this is as far as driving from Taipei to Kaohsiung. Data transmission latency is extremely high. Bandwidth is too narrow because the roads aren't wide enough. The amount of data that can be transported per second is limited. The Ferrari can only drive slowly on small roads. Power consumption is too high. The longer the transmission distance, the higher the voltage required and the more waste heat generated. Thus, the concept of heterogeneous integration emerged. TSMC said, since the roads aren't fast enough, let's just strip the shells off the GPU and HBM and build them into the same luxury apartment. This is CoWoS, and the foundation of this apartment is our protagonist today, the interposer. First, let's look at the most authentic and earliest famous version, CoWoS-S. The S here stands for silicon. Its foundation is a complete silicon interposer. Why use silicon? Because the chips themselves are made of silicon. Advantages: it can use the same photolithography technology as semiconductor manufacturing to etch circuits with extreme precision. How fine? Its line width can reach 0.4 microns or even finer. This allows for tens of thousands of channels between the GPU and memory. Data transmission is like instantaneous teleportation. Representative works. This is why NVIDIA H100, A100, and Google's TPU chose it. Weakness, but the S version has one fatal flaw: the reticle limit. Currently, the maximum exposure area of a mask is approximately 858 square millimeters. If you want to make the chip even larger, the silicon interposer would crack or fail to expose. Furthermore, a whole piece of large area silicon is very expensive. This is also one of the reasons why AI chip prices have skyrocketed to the heavens. Next is CoWoS-R. The R here stands for RDL redistribution layer. TSMC found that some customers don't need such extreme transmission, but they want larger areas and lower costs. So the R version discarded the expensive silicon foundation and switched to organic polymer materials. Key technology: it utilizes RDL technology to route circuits directly on the organic substrate. Advantages: organic materials are flexible. They can absorb thermal expansion and contraction stress during operation. This is very important in large-scale packaging. More importantly, its cost is much lower than the S version, and the production process is faster. Application scenarios: it is suitable for those slightly sensitive to cost, or for packaging sizes that need to exceed the reticle limit, like communication or mid-range chips. Finally, let's talk about the most futuristic version, CoWoS-L. It is a hybrid tech between S and R, facing chip monsters like NVIDIA Blackwell. S is too expensive and small, while R's transmission isn't fast enough. So TSMC came up with a brilliant idea: local silicon bridges. Concept: the main foundation uses cheap RDL material like the R version, but between GPU and HBM, or between GPUs where high-speed racing is required, I precisely embed a tiny silicon bridge with extremely fine circuits. Advantages: this allows the chip to break the reticle limit because the foundation is organic, yet still possess silicon-level transmission speeds. It perfectly resolves the contradiction of wanting size, speed, and affordability simultaneously. Strategic significance: this is why people say CoWoS-L is the key technology moving toward wafer-level systems. You might ask, Intel has EMIB, Samsung has iCube. Why is everyone still lining up for TSMC? The answer lies in the ecosystem and yield rate. TSMC doesn't just provide packaging and back-end advanced packaging within the same site. This is what is called Foundry 2.0. When chips are made at 5 nanometers or 3 nanometers, they can go directly downstairs for CoWoS packaging. This greatly reduces logistics risks and testing costs. Not to mention TSMC has accumulated over a decade of data on CoWoS. That yield stability is a moat that current competitors find hard to reach. So, next time you hear about AI capacity shortages, you will understand it's not just a wafer volume issue, but a race of trade-offs and yield tuning. Among these three CoWoS technologies, CoWoS-S secures the baseline of performance. CoWoS-R opens up space for cost reduction, while CoWoS-L points the way for future giant chips. In this new semiconductor racetrack, it is the protagonist determining whose computing power is stronger. Which type of CoWoS do you think will dominate in the future? Or will even newer technologies emerge? Feel free to leave a comment below to discuss. If you like this kind of simple tech deep dive, don't forget to like, subscribe, and turn on the notification bell.